Howdy there, kids. So what you're looking at right now is a compass. So I went to Google and I searched up compass, and this is what I found. This was my favorite picture, so here it is. So this one actually shows pretty clearly what I'm trying to get at. The next thing we're going to learn about, which is related to the cosine law, although it's just kind of a trigonometry thing in general, is how to read a compass. So this is not really something that's too mind-bendingly difficult. It's one thing I really want to emphasize here is when you're talking about doing some sort of navigation with a compass, you'll notice the way the degrees are labeled is different than what we've been doing in class with our standard position angles. So normally we start with what would be considered east. I guess that would be the positive x-axis, and we would call that 0, and we'd actually move in a counterclockwise direction. Turns out when you're using compasses, north is 0, and as you go clockwise, you're going to increase your degrees. So it's not really that difficult. It's just something to be aware of when you're doing questions where navigation is mentioned, or bearings, or a compass, or something like that. You just have to know that the way the angles are measured is starting at north, and then you go from 0 from there, and then you go clockwise. And there's a couple other different notational things that we'll look at. So continuing along, so where we were at in part 1 was we did this example. Part 2 here, we're just going to continue and do the examples with bearings. So bearings are pretty simple. Bearings are angles. If only a degree is given, which is pretty typical for a bearing, we'll just say like someone's moving at 20 degrees. Usually what that means is we're talking about an angle that starts at north and it goes clockwise. So a bearing of 60 degrees would be going from here and going all the way across, and then 240 would be this, 330 would be that, and so on. Okay, so nothing too crazy complicated. Just be aware that is what bearings are all about. Now, there is one thing I want to mention. The notation of bearings is it going to pop? No, it's not going to pop up, so I'm just going to write it down. There's a couple different types of notation. So if you are doing what the textbook does, a bearing of 60 degrees, you could leave it as just a bearing of 60, and for some reason they like to put a 0 in front sometimes, but it's just 60 degrees. What you can say is you can say that you are heading north and then 60 degrees east. So you can do something like that. I personally don't like that notation, but that is one type of notation that is commonly used, where you start with your main direction and then you write what you're deflecting off by. So this is sort of like the main direction, and then this would be, I'd call this like the deflection away from it. What's pretty common in physics is you will say something that is same as you'd say, there's two ways of doing this in physics actually, but I'll just tell you both of the ways. You could say 60 degrees and then you would say east of north, and I personally like this kind of notation better because it's a little more clear what's going on. So you're saying 60 degrees east of north. So you were going north and now you're deflecting 60 degrees east of that. Of course, in physics, if you have taken physics, you may be aware of this, and we actually would generally write, or you'd even say 30 degrees north of east, because you tend to use the smaller angle when you're doing that. Anyway, there's a few different ways you can do directions. The way the textbook uses is this first method here, the n 60 degrees east, which is not my favorite because unless you just happen to know what that means, it's not super clear. And then of course this is what's typically used in physics. So just be aware there's different ways of doing that. Oh, and one other tiny little thing, if you ever see like northeast, this is equal to like north 45 degrees east, or 45 degrees north of east, or east of north, it doesn't really matter. So if you're ever going to see like northeast, it's exactly a 45-degree angle. Okay, so let's do a little problem here. These problems are nice and meaty and they involve a little bit of geometry, so we're going to go through this one in some detail. So a group of hikers walks 8 kilometers at a bearing of 80 degrees, then they walk 3 kilometers at a bearing of 20. I guess they get lost or something because a helicopter must fly from their starting point to pick them up at their end point. What direction and distance must the helicopter fly? So I'm just going to write down a very rough sketch, and then I'm going to make this better. So we're going to start with this idea. Okay, so here's northeast, south, and west. Never eat soggy Worcestershire sauce. I don't know. Okay, so if we're going at a bearing of 80 degrees, that means we're going off in an 80-degree angle here from north, so we're going off kind of like that. And then if we're going 3 kilometers at a bearing of 20, that means at this point here, we've now changed our bearing and we're going at 20 degrees. So we'd have to draw a new sort of set of axes here, and we'd be going up at about a 20-degree angle. Right? So that's the idea. And then what happens if this is your start and this is your end? Helicopter's just going to go straight across. They're not going to follow your exact path. So what we've got to do is we've got to figure out that angle. So what I'm going to do is I'm going to draw this. I'm going to draw this really nicely because we're actually going to need a nice diagram here so that we can do some geometry. So here's our first set of coordinates, and I'm just going to draw like this. I know that's not exactly 80 degrees, but it's close enough. So we go all the way here, and we've walked for 8 kilometers. So I'm going to give that a length of 8. And then over here, I'm going to sketch another set of axes because at this point I need to measure 20 degrees from north. So we're going to go up 3 kilometers. So maybe something sort of like that is going to give a length of 3, and that's right in there is a 20-degree angle. All right, and then I'm going to switch colors here to show that the helicopter is going to go from here to here. So this was the start, and then this was the end. Okay, and then the question is, what direction and distance must the helicopter fly? So I'm going to call this, we'll make it X because that's pretty typical in math. And we've also got to figure out what direction and distance. So of course we're talking about bearings in this case. So we're going to make this a bearing. So we've got to figure out this angle in here. Some of you might be tempted to say, isn't that 80? But no, it's absolutely not. We can see that it's a little bit less than 80. Okay, so I could even put an arrow at the end of that if I really want to be clear on the direction. So what we're doing is we're essentially solving this triangle. So we know a few things about it. We know 2 of the sides. Do we know any of the angles inside the actual triangle? Because what I've done here is I've made myself a triangle. And I've got to figure out, so I'm going to maybe just draw my triangle down here. What does my triangle actually look like in terms of the angles inside? So here's X, here's 8, and here's 3. I don't necessarily know what any of my angles are. I'm going to call them A, B, and C. That's a funny looking B. Let me fix that. But I don't necessarily know any of my angles. So I have a 20 degree, but you'll notice that 20 degree is just up there in this corner over here. That's not an interior triangle angle. And I have an 80 degrees, which goes like this, but that's not going to be very much help either. Because that's not an interior angle. So these problems involve a little bit of thinking and creativity and mostly geometry to figure out what angles I actually have. There's not a lot of information here on angles A and B, but if you notice angle C, this one we actually can work out. And the way we can work this out is we go back up to our diagram here, and we know that this little bit here, that's a 90-degree angle. We know we've got a 20-degree angle up there. The only thing we have to do is figure out what this little angle is, and then we can add up all 3. So this little angle up there, I'm going to show you a little geometric trick. Well, it's not really a trick, it's just sort of a thing, a fact about geometry. When you have 2 parallel lines like this, and you have an angle here, the angle here, these 2 match, and you could put a line to them to say they match. So this is, it's called alternate interior angles, but I call it the Z-angle theorem because it's kind of makes Z's and stuff like that. So what we have to do is we just have to decide what this angle in here, what is this? This angle is actually really easy to get. I know that from here to here was 80 degrees, so from here to here was 80, so this is a 10-degree angle because they have to add up to 90. That means that this guy is also 10 degrees. And what that means is that this angle here is the sum of 10 degrees, 90, and the remaining 20. So this is 10 plus 90 plus 20. And that gives me a 120-degree angle. Okay, so if you don't have an interior angle in your triangle, you'll have to do a little bit of geometry that way. But once you've done that a couple times, it's not too hard. So this is super. So once I have this, I have a side, and then I have an angle in between, and then I have another side. This becomes a sassy triangle. If it's a sassy triangle, then that's usually a good hint that you can use cosine law. So if I want to figure out the distance the helicopter goes, which is x, I'm going to use cosine law, and I'm going to write it like this. You know what? Let me just change that. I'm not going to call that x. I'm going to call that little c, because that's the notation I'm using here. And that's little b, and this is little a. So we're going to figure out the distance, and we're going to use the cosine law. Okay, so we're going to go, I'm going to move this guy, I'll keep him right there, I guess. Okay, so we're going to go c squared equals a squared plus b squared minus 2ac 2ab cosine c. Okay, so c squared equals, now the rest is just do some arithmetic, not really that hard. And that's cosine of 120 degrees. So c squared is equal to, I'll even just skip the steps, I'll just figure out what c is. So we get our calculator, and then we turn it on. We make sure our mode is in degree, so we go over here to degree mode, and now we'll just go 3 squared plus 8 squared minus 2 times 3 times 8 times cosine of 120. Don't worry, your calculator will do the correct order of operations for you in this case. So we'll do all this and we'll get 97, and then if we want an actual numerical answer, like a decimal, we can do that. So we'll get c squared equals 97, or c equals the square root of 97, which is approximately 9.849, and it would be kilometers. Does that look about right? You walked 8 kilometers this way, then 3 kilometers up, and you're kind of taking a bit of a shorter path because you're not following the bend that the hikers took. And that seems reasonable, so 9.849 sounds like something I can get on board with. Okay, now the question is, what direction and distance must the helicopter fly? So we've got the distance, but we need the direction. So in order to figure out the direction, now we've got to work out, okay, so here's our coordinates. Well, that's just terrible. Let me try that again. Here's our coordinate system here, and what is our actual direction? So we've got to figure out this angle in here, and I'm going to call that angle, I'm going to call that theta. So what I can say here is the angle, or the bearing, I guess, what I can say is that my angle A, which is inside, I could say that angle A plus theta is going to equal 80 degrees. And I know that because my original line, like this side down here, that was an 80-degree angle from north. So theta plus whatever A is would have to add up to 80 degrees. So I'm going to go theta equals 80 degrees minus angle A. So my job right now is I have to figure out angle A, and if I know what angle A is, then I can go ahead and I can solve for the rest. So grabbing angle A is not super difficult. What I'm going to do is I'm going to solve it using, I could use cosine law because I have all 3 sides, but I'm going to use sine law. So I'm going to write sine A over A equals sine. Okay, I don't know angle B, so I can't use that, but I'm going to go sine C over C. So angle A, I'm just going to do the rearranging here, will be inverse sine. And then I'm going to move side A up here, so I'm just going to write it in because I don't have a lot of room. So side A is 3 multiplied by sine of angle C, which is 120. and then it's divided by the side length of C, which is, you know what, it's probably better if I just write root 97, because that's going to give me a precise answer. So this turns out to be, so now I'll go up here, I'll go doing it all in one calculation, sine inverse, and then I'll go 3 times sine of 120, close it up, divide by the square root of 97. Now I'm just going to use the answer here because that's the last answer actually recorded was the square root of 97. So that's fine if I have it stored on my calculator. And what I get is an angle. I get an angle of 15.29. So I'm just going to write this as 15.3 degrees. Does that look approximately correct? Given my diagram, it's like that little sliver in there. That is 15.3 degrees. That seems like that could be reasonable. Okay, so now I take this and I just go back up here and I go 80 degrees minus this. And what I get is I've got my helicopter having to fly at, I guess that would be a 64.7 degree bearing. Okay, and then I'm traveling 9.849. Maybe that's a little excessive. Maybe I'll just round that to like 9.8 kilometers. Tiny little note in case anyone's wondering, when it comes to round this, sometimes people will say, well, don't use that 9 to round this to a 5, and then it's 9.85, and then you use the 5 to round that to 9.9. No, that's not how rounding works. You always just simply use this guy here, and you're going to round based on whether that's a 4 or a 5. Okay, so we go 9.8 kilometers at a bearing of 64.7. I guess this is a word problem, so you might consider writing out something like that, but I'm running out of room, so heck, I'll just figure this out here. Let's write it. Okay, so must travel at, must travel, I guess the best way of writing this, must travel 9.8 kilometers at a bearing of 64.7 degrees. Cool, okay, there we go. It's good practice to write it out. Okay, that's actually it for this one. So there's some questions like this in the homework, and I'll probably give you some extra questions. These ones can take a little bit of work to do, but once you've done a handful of them, you sort of get the main idea. All right, that's it. Thanks for watching.